So once you open this previous regression example, so this is the y and x series that the author or something like the generated randomly variable series. So you can try to plot your series and see what happens. So maybe you open them as a group, right? Open them as a group, and then you just simply just view, and then you just open them and then view as a graph. Then maybe you can separate them to become multiple graph to have two different graphs. So now you can see your y series actually is trending upward, right? And then your x series is also like a roller coaster, right? Going up, down, and up and down. So it have a tendency that actually you having your series actually consists of the time varying mean, right? Because the two have a mean, right? Time varying mean as well as the variance. So the variance as well as the mean value for this x series and the y series actually is non-constant. So for this, I would like to replicate the result just now. If you just simply run the y on the x, and then open them as an equation, right? Then you use the method least square, and then you click OK. So you already replicate the result just now with the significant x variables together with the 0.33 r squared and very low W-Wilson steady state. Actually, the result here is spurious because you have a rule of thumb here. The r squared is greater than the W-Wilson steady state, right? And how are you going to solve it? You can try to first difference, right? Because like we said, this is follow the random walk. If you first difference, the series actually becomes stationary. So what is the issue here? Issue here is for the non-stationary y, if you request on the non-stationary x, then you will come up with a spurious regression. So in order to avoid this spurious regression, we can first difference the series. So first difference the y series, and then you request on the first difference for the x series. So how to do that? You can go to estimate and then just click on the d, right? The d for the y. Maybe I put the d first, see whether workable or not, and then d for the c. Or d for the x, sorry, it's not fine. No worry. So you d in a bracket for the y series, and then d in a parenthesis for the x series together with the constant. So no need first difference the constant here because cannot first difference the constant. So here method least square, then you click OK. So you already first difference for your y series as a dependent variable. Then you request on the first difference for your x variables. So what is the return your result here? Your t-steady state become not significant. Then you have a very low r squared. Then together with a very high W-Wilson steady state. So actually you request the stationary y series on the stationary x series. So these are your findings. So the result here actually is not spurious, not spurious. So this is the idea behind the stationary random walk models. So so actually how we can test it? How we can test? So actually we have a formal test to test the series whether is it uniroot or no uniroot. So what is the difference here? So actually stationary refer to no uniroot, and non-stationary refer to uniroot. Okay, so no stationary means refer to uniroot. Actually, we have a more formal test to test for this stationary. The original idea is proposed by Dickey and Fuller. So we evaluation is a BF test. So this Dickey-Fuller come up with the test equation. Actually, these are the three different models proposed by Dickey-Fuller. So these three different formats. So it's X means the first difference for your YT, and then request on the YT minus 1 together with the absolute. Means this is the model. So it means that this Dickey-Fuller said, okay, the dependent variable is first difference for your Y, and then request on the YT minus 1. So this is the test equation proposed by Dickey-Fuller for the pure random walk models. So how about if your series follow the drift, right? So there is a possibility. So this Dickey-Fuller proposed another models with the same dependence, with the same independent YT minus 1, but together with the intercept. So with the drift here, intercept. And then how about the train? Because some series follow the train, right? You cannot ignore the train component. So for the train component, so the Dickey Fuller proposed another models with the changes in the Y, or the YT minus 1 together with the intercept, together with the time train. So you can see three different types of the models here. So the T refers to the time or the train variables. So again, so this actually is testing whether the series is it follow the stationary or non-stationary. So before that, we have to clear. So have you heard about the I1 variable? Maybe all of it. So I1, I0, I1, I2, what's that? So I1, it means that the value in the parentheses is referred to the integrated properties. Okay, this refer to integrated properties. So it actually is a ID. So it's an integrated property of the series. If your d is equals to 0, what it means? It means that if the d equals to 0, we don't need to do anything. The series already stationary. So that's why we call the variables actually, or the series actually is I0. So the first category. If the series have to first difference only stationary, first difference the series only stationary, then we call it as an I1 variable. If the series have to second difference only stationary, then we call the variable as an I2 variable. But very seldom, right? Because for example, at the GDP, it's very hard to get I0 because the GDP is a time, follow the time train, right? It's out the train. So if we first difference the GDP, it might become the changes, right? Become the growth rate. So we will have a possibility of the stationary for the GDP series, the growth rate in the first difference. So it's seldom to have an I2. Actually, if can we have an I3? Sure. It means that difference 3 times, only stationary, only have the constant mean and constant variance, very seldom, right? Very rare. This one is very rare. This one also very rare, but it can be happen for the I2. So mostly the macro variables will be have the I1. Mostly except the growth series. Except the growth series. It means that the growth series like the economic growth, like the inflation, because it's the changes, right? Changes in the CPI. So the growth series, we might have the I0. We might have the I0. So for example, like the growth series. So these the things. So like for example, like the economic growth, like the changes in the GDP, right? Changes in the GDP, changes in the CPI, we might have the I0 series. I0 series means that we don't need to do the first difference, the series already stationary. Because it means that we don't need to first difference the variable, the series already stationary. This is called I0, right? So these are the several cases, I0, I1, and I2, I3. So now, so what is the hypothesis for this unit test? The hypothesis for the unit test is unit as a noun. Unit as a noun, again alternative stationary as a alternative. Unit as a noun. Unit, because we are testing the unit as a noun. So the first noun is there is a unit. There is a unit because this coefficient equals to 0, right? If you still to reject, means there is a unit. It means there is a unit. Against alternative, the series is stationary, means no unit root. So another word is called stationary. No unit root or stationary as an alternative. So this is our hypothesis. So H now is there is a unit root against alternative means that H1 is no unit root or stationary. Then a little bit difference is this. You see this follow the t statistic, right? Actually not follow the normal distribution. So do not follow the normal t distribution. So we need to compare the ADF statistic or the degree freedom statistic with the simulated critical value. Because it's follow the tau statistic. So you can we have to refer to the different statistic table to compare the statistic. So how about the augmented Dickey-Fuller? So this is called Dickey-Fuller, right? Dickey-Fuller test equation. You can see change, for example, like this one, changes in the y, on the intercept, on the time train, on the yt minus 1, and also together with the residual. So how about the augmented Dickey-Fuller? For this augmented Dickey-Fuller, you have changes in the y again, got intercept, got time train, got yt minus 1, together with the lag for the changes in the y, lag for the dependent variable. What is the difference between the NDF and the Dickey-Fuller? It's the last variables. The last variable. So again, yeah, you see here we have the changes in the y on time train together with the intercept, together with the yt minus 1. But for the augmented Dickey-Fuller, we have the changes in the y, intercept, time train, yt minus 1 still remain the same, right? But the difference between the ADF and the Dickey-Fuller is with the lag for the dependent variable. So what is the purpose for this? So for this lag dependent variable is used to accommodate the serial correlation in the Dickey-Fuller test equation. Serial correlation. So the Dickey-Fuller test equation actually suffering from the serial correlation. Suffering from the serial correlation, especially you have a yt minus 1 here. So that's why there is an augmented Dickey-Fuller version. It's an improved version from this Dickey-Fuller. That's why called augmented Dickey-Fuller to accommodate the serial correlation in the original test statistic, but incorporate this lag for the dependence variables. What is the dependent variable? The changes in the yt. So the changes in the yt, and then we impose. Actually, the critical part for this augmented Dickey-Fuller is the lag length, right? How many lag you need to put inside to decide for the n? How many n? 1, 2, 3, right? So depends on your model selection criteria. So what model selection criteria we learned before? AIC, SIC, right? So there's the model selection criteria to guide us how many lag to put inside to get rid from this serial correlation in order to get the correct augmented Dickey-Fuller test statistic. And these changes in the yt minus 1 is what it is. Actually refer to the change of value for the yt minus 1 minus yt minus 2. So accordingly. So this is one of the example. Example number 1, log series for the GDP. So again, it's follow the time train, right? Or R. So it's very obvious that going to violate the stationary property. Because for the stationary property, we need to have a constant mean at least, right? At least. And also, if you don't know about the variance, it should have a constant mean. But it's very obvious that the mean is not constant and increasing over the time. So, how are we going to test it? I can use the augmented Dickey-Fuller test to test it. And it's based on the maximum lag 10. Then this is output we're going to generate later. What is the maximum lag 10? Because based on our observation, the EBU suggests that there is only 10 lag can be used to get rid from this serial correlation. And out of this 10 lag, the maximum lag is 10. Then the model selection criteria suggests to only have 1. to accommodate the serial correlation, only one. And this testing the constant with the train. Constant with the train. So this is the third model, right? Third model. So the third model is referred to this one, right? This one, right? Why? It means with the time train and also the constant. This is the third model. So how we can get the steady state? You mean the steady state here? You curl this one, this is our interest, right? We curl this one. What I need to open is the first one. No. Stationarity. Data lecture 8.
Okay.
Data lecture 8. On this stationarity, then once you open this file, there's a random walk one, right? It's actually our examples, right? Here on that. So here, log for the GDP is trending upward. Trending upward. So how about first difference? If you first differentiate, you look at the graph. Well, we have something like fluctuated around the mean, right? Yeah, so there's a potential to have a stationary series. By the way, how are we going to test it? You can click on the LGDP, then go to View, Unit Test. You can go to View, click on the Unit Test, and refer to Standard Unit Test. Because there are three options, right? You have Standard Unit Root, you have Breakpoint, you have Seasonal. So click on the Standard Unit Root. So the test type. So once you click on the test type, when you scroll down, the first one is an augmented Dickey-Fuller. So you don't have a Dickey-Fuller because Dickey-Fuller is going to suffering from serial correlation, right? That's why Illustrate already give you the augmented Dickey-Fuller. Beside the ADF, augmented Dickey-Fuller, we also have this ERS, Phillips parents, KPSS, and also the unpaired. So these are the list of unit tests that used to test for the stationary, the test for the unit, test for the stationary. Then you're going to ask which test you should rely on, right? So here we just introduce you the augmented Dickey-Fuller. Actually, we also have the Phillips parent. Actually, this ADF and Phillips parents are the two unit tests is introduced to solve the serial correlation suffering. It means the serial correlation in the Dickey-Fuller. So, but they're based on the different idea. One is just based on the Dickey-Fuller, the other one is extension. So actually these two have a complementary, just complement each other, ADF and the Phillips parent, just for information only. And because of the power of the test, power to reject the H now as a unit root, KPSS come in. KPSS come in to propose that actually we have a power to reject the unit root now. So the KPSS come in, propose the Lagrange multiplier test, which to accommodate the power of the test. So KPSS is another test. But the KPSS will have a different H now. KPSS has a stationary as a H now. Stationary as a H now. A little bit different, right? Because to accommodate the power of the test. Then recently, not so recently, 2021 and 2001, well, I think 30 years ago, a parent come in to propose another statistic. So these are the different statistics to complement each other, okay? So let's take a look at Dickey-Fuller and test for the unit root in the level. So what is this? This is for I naught. What the test? Is there a possibility for my GDP series is I naught? If the series is stationary with a level, then I say that my series is I naught. If your series is stationary, based on the second option, first difference only stationary, that is called I1. If the series have the second difference only stationary, then the series is called I2. So level, so normally you will start to test I0. To test I0, is it level or stationary? So I want to test I0. Then include in the test equation. there are three models here. None is a pure random walk, right? The pure one, and just with the drift intercept. And the third case, train and intercept. So these are the three type of random walk models, right? In the test equation, either none, pure one, with the drift term, and also the train with the drift term. So these three, right? Pure random walk with the drift, and just with the drift and the train. So you are testing three different models. And how about the M? Because we need to decide the M, right? For this augmented Dickey Fuller, where we set the number of M, the length for the leg dependent variables on our right hand side. So how many leg here? How many leg? Is it 1 leg, 2 leg, 3 leg? So it depends on the model selection criteria. So here, that's why it's automatically selected based on the information criteria. So by default, it's the squash information criteria. So actually logic because we only have 61 observation. It's quite small sample size. So there is a less penalty if we use the SIC. Let's say if we have a high or very huge sample size, high frequency data, is advised to use AIC. So this is like what we discussed in the previous class. So SIC, to select the number of leg to get rid from this serial correlation. Then you click OK. Once you click OK, actually replicate your result, right? Replicate your results. So my dependent variable is the changes in my GDP series, right? And then this one. Changes in my GDP series together with the trade, vector 0 refer to constant, and then time trade refer to the trade here, and then the LGDP T minus 1 here, right? And also the lag 1 period for your dependence variables, this one. So this is the model, this is augmented Dickey Fuller. So how many lag? Only one. Only one, right? So this is the third test equation proposed by augmented Dickey Fuller. So here, negative 2.768, right? So this is a test statistic. We cannot rely on this p-value. This is a test statistic, negative 2.76. Negative 2.76, we have to compare with the critical value proposed by Dickey Fuller, which is this one. And also same like the files I share in the spectrum. Augmented Dickey Fuller files, this one, right? So this is the critical value simulated by the Dickey Fuller. It's used to compare with the test statistic, but it is very nice, straight away provide you together with the critical value. It depends on the observation, sample size. Okay? So these are the three different models. You have the pure random walk model, and the random walk models with just with the drift, and also with the drift and the time trade. So different model will have a different critical value. So now, how are you going to do your conclusion? So this one is actually greater than your critical value, right? So you fail to reject. So fail to reject means what? Fail to reject, your H now has a unit root. If you fail to reject, it means that your GDP has a unit root. So unit root. So another way to look at the result is based on the p-value, 0.2144, not significant. So do not reject the null. So you can conclude that your LGDP is non-stationary. Okay? So let's take a break, then we come back to discuss another whether is it first different stationary or not.
What do you understand from that? 吃到熟悉的味道吗？啊，我吃到熟悉的味道了。是我们在environment 的时候刚吃的味道。发哥，不要钱，没有啊。